superconductivity. Now, this is not exactly the field of research, although it's been used extensively from nuclear physics on the microprobe into the direction of solid state physics. So we look forward to great interest to hearing Dr. David Jamieson on the subject of superconductivity.
Thanks, Tony. Okay, well, the new superconductors. It's been an extraordinary pace of development occur in the field of superconductivity since 1986. And it's time now that the hype has died away somewhat to take a bit of a look at these new superconductors and see if they will promise a new industrial revolution, because they are so potentially, a superconductor is so potentially very useful. So I shall try and answer this question tonight as to whether we will look for a new industrial revolution, such as the revolution in transport with the magnetically levitated train. Okay, well, our story gets underway back really at the turn of the century. I'd like to start with a historical introduction to the topic, and then move on to talk about how a superconductor works, because until quite recently people really didn't understand the new superconductors. They seem to be too good to be true. And then I'll talk a little bit about the new superconductors and what their potential applications are. Okay, so step one, if you're looking for a superconductor, you've got to make things very cold. And this is easier said than done if you're dealing with very low temperatures. And the standard way of making things cold, of course, is to compress a gas, and of course it gets hot. So you pump all that heat away, and when the gas is nice and cool again, in its compressed state, you let it expand, and as it expands, it then cools. And this is a bootstrapping process, because what you can do is you can start with a gas which is easy to liquefy, and then you can use that gas in its liquid state, cold liquid state, to then cool the next gas down the line, and so on. You can work your way all the way down the line to very low temperatures. And this is some apparatus that was used for this procedure, and you can see the nested series of dewars here, where each successively cooled gas, the liquid of each gas was located in order to take the temperature down successively. We'll come back to that later on. But before I start talking about what goes on at these low temperatures, I want to just introduce the temperature scale that we scientists use. You're all familiar with the Celsius scale, which is the one we use for the weather report, and it's usually adequate for Melbourne in the winter time, although I had my doubts this morning. But anyway, room temperature is say roughly 20 degrees on a good day, and this is equivalent to 293 Kelvin, which is the temperature scale that has its zero at absolute zero, the temperature below which everything stops, pretty much, as far as quantum mechanics lets it. So, of course, there's the freezing point of water at 0 Celsius, which is 273 Kelvin, and then way down here you begin to liquefy nitrogen at 77 Kelvin, and this is minus 196 Celsius. And most of the story tonight takes place way down in this blue region, and this shows a blow-up of what goes on down there. And you can see that we have, here again is the liquid nitrogen at 77 Kelvin. Oxygen liquefies a little bit warmer, and then nitrogen freezes down here, oxygen freezes. Finally, way down here, 20 degrees above absolute zero, hydrogen liquefies, and then shortly afterwards solidifies. And then finally, the last gas to be liquefied was helium, because it's at only 4.2 degrees above absolute zero. And this was quite a challenge, and the fellow who succeeded in liquefying helium first was Cameline Owens. shown here in about 1908. He was a pioneer in the low temperature research. The trick was, of course, to proceed by chilling the compressed helium with each of these gases down to finally cooling the compressed helium in liquid hydrogen. In those days, 1908, it wasn't easy to get hold of helium. You couldn't just ring up CIG and order a bottle of helium. Helium had only just recently been discovered, after all, in the spectral lines of the sun, and it was extracted from terrestrial sources by heating the ores of radioactive material, because radioactive material decays by alpha particle decay. The alpha particle collects a couple of electrons and turns into a helium gas molecule, and you can extract that helium gas just by heating the ore. And in fact, one of Onus's rivals in Britain, he was working in Holland, was James Dewar, who of course invented the Dewar. He obtained his helium not by heating the mineral ores of radioactive material, but by collecting bubbles of gas that came up out of Bath Spa in the town of Bath in England, and carting it out back to London for his experiments. But unfortunately for him, this source of helium was contaminated with neon, and he did not succeed in liquefying helium before they did in Holland. Okay, so once you've liquefied the gas, what do you want to do with it? Okay, so that was a significant technological achievement. Here we see, to give you an idea of the apparatus required, you can see all the piping and what have you, and this is the canister of the tank of helium that the trusty assistant, whose name was Flim, is adjusting, who was responsible for building all this apparatus. And this is the one day a month which was called the Helium Day, which was when they were actually allowed to do experiments with helium itself. They didn't have helium days every day, just special days where they could use the actual helium. Okay, so having cooled the gas down, liquefied it, it's then available for doing experiments at these very low temperatures. And at about this time, the early developments were going on with nuclear physics by Rutherford, and some of the heroic early scientists were trying to develop atomic models for solids based on the new atomic theory. And it was regarded, and of course here is an atomic model of a solid showing a whole bunch of atoms held together with molecular bonds in a square lattice, in a cubic lattice. And in those days, of course, nuclear physics was not so readily available as an experimental method. And so how do you test what goes on inside a solid? How do you test your model of what goes on inside a solid if you can't bombard it with protons or alpha particles or something? Well, the answer is you feed electrons through it. You feed electrons through it and study how they scatter in the solid. And in particular, in Holland, they were interested in studying the vibration of the solid as a function of temperature, because of course at room temperature this thing's going like this, and all the atoms are wobbling around all over the place, and then as you cool it down, the vibrations die away. And so if you pass some electrons through this when it's hot, they scatter all over the place. And in other words, there's some resistance to the flow of current. But if you pass electrons through when it's cooled down and everything's nice and quiet down there, you can drop an electron through there and it doesn't hit anything very often. So the resistance of the solid gives you a good indication of the way the material is behaving at low temperatures, and it's much easier to test your models when things are nice and simple, nice and cool, not moving around very much at these low temperatures. So the theorists studying this began making some predictions of how the resistance would behave at the low temperatures. Yeah, please come down and take a seat there. That's great. Okay, so here's some theoretical predictions based on some early measurements around the temperature of liquid hydrogen, about 20 Kelvin above absolute zero. And there are a few data points here and a few dotted lines indicating the way they thought the resistance would go as the temperature was lowered further. And of course we have to remember that even at absolute zero, the atoms are not perfectly stationary, and they thought that maybe the resistance would go down and level out according to their theoretical models. And so in order to really test these theories carefully, you needed to make sure you started with a metal that was very pure, and platinum and what have you, gold, were used in these experiments here, but they're difficult to make as pure as you would like, because once you get down to these low temperatures, trace amounts of impurities are going to cause you a problem. And I mustn't forget to do a demonstration. I can reenact this right here in the lab. First of all, I need, well, I've got some copper wire here. I've got some copper wire wound into a coil, and just to give you an idea what goes on when you cool things down, I'll cool this copper wire down and we'll see how the resistance changes. Now I've got a little light bulb connected up to this copper wire, and I think I'll have to turn the lights down a bit so you can see this. It's a very long piece of copper wire, and so the, let me just adjust that a bit, yeah, it's a very long piece of copper wire, and so the resistance is quite high. And so my, my light bulb is not glowing terribly much. In fact, you can hardly see it because there's not very much current getting through there. However, this is not the situation if I lower the temperature, which I can do quite conveniently. Oh. Oh. Of course, my dewar is at room temperature, and the nitrogen I just tipped into it is at 77 degrees absolute, and so the nitrogen's not too enthusiastic about that, but it's just calming down a bit. Yeah, okay. Watch what happens now as I put my coil of copper wire here into the nitrogen. You can see the as the copper cools down, its resistance is decreasing, and the bulb is getting a lot brighter. My feet are getting very cold here. Hang on. Let's move that a bit further away. But by now, the thermal vibration of the copper atoms in the lattice has slowed right down, and the resistance has really dramatically fallen. You can see the light bulb is now glowing quite brightly. Okay, so this is a very nice way of probing the internal structure of the copper. See how it behaves at these low temperatures. So, but of course, as I said before, the contamination is a problem. If you aren't careful to start with very pure material, your results can be perturbed, maybe not reproducible, because the contamination, the trace impurities, can interfere quite significantly. So, what was done, instead of using platinum or gold, they adopted mercury, because mercury you can distill and distill and distill in order to purify, and you can make mercury very much more pure than you can make lead, platinum or gold. And so the big day came. They made little mercury capillaries by tipping mercury into glass tubes and then freezing it, being very careful to avoid contamination. This shows one of the mercury capillaries used in the experiment, and it's all coiled up and put down inside the helium dewar with leads connected to it to measure the resistance. And they began to lower the temperature, and of course if you've got a little bath of liquid helium, you can lower the temperature below its boiling point by just pumping away the vapours that above it to lower the pressure, lowers the temperature, and this was the result. They followed the resistance of the mercury down, 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 until suddenly at 4.2 Kelvin above absolute zero, the resistance suddenly plunged right down to below the sensitivity of their resistance measuring apparatus. They could only put an upper limit on it, and this was quite startling, because instead of the nice gradual decline that they were looking for, there was evidence that something new had happened to the material and that it had gone through some kind of phase transition. And there are a lot of other strange phenomena associated with this as well. Once they realised what was going on, that there was something new here, they began to investigate it. And the first thing to do was try and measure what really was the resistance down here. And so they did that by raising the current that they were using to measure the resistance of the mercury filament, and very strange things began to happen, because when they raised the current above a certain level, suddenly the resistance jumped back up to where they were expecting it to be. And this was very, very puzzling, but nevertheless, and that's going to have significant implications for what we're going to discuss tonight, but nevertheless they soon recognised that the resistance had indeed disappeared, and they had discovered superconductivity. Now, this was fantastically exciting, of course, this new phenomenon, and so quickly they broadened their studies to look at a whole lot of other materials, and before very long they and other workers in the field had discovered other materials that have this property of losing their resistance at low temperatures. And today we recognise that pure elements, there are a large number of pure elements that are superconducting. The edges are unimportant. Shown here in this periodic table. We see the mercury down here. Pretty soon after mercury was found lead, and so on and so forth. Now, we recognise that the materials which are the superconductors are not the ones which tend to be the ones which have the lowest resistance at room temperature, copper, silver, gold, for example. And this is related. This is no accident. And I've just given you the edited highlights of all this data down here. Niobium metal is the best. It goes superconducting at a rather warm 9.5 degrees above absolute zero. And nature has played a little trick on us here. The next best one is technetium, which of course is a radioactive material, and there is no stable isotope of technetium in nature, so it's just a little joke here. And lead is not bad, lanthanum's not bad, mercury's not bad, and there are a few others around 6 Kelvin above absolute zero. Now, given a superconductor, what would you want to use it for? Well, obviously something which will transmit a current with no resistance has a lot of technological applications, particularly when it comes to generating strong magnetic fields. Now, how do you normally generate a strong magnetic field if you don't have one of Professor Opat's little neodymium boride magnets or whatever they were? Well, you have to use a solenoid, an electromagnet. And here I've got a solenoid, which is I've got wired up to a power supply, and as I can turn the current on here, and you've got a digital readout here of the magnetic field in this solenoid. Now, let me first of all null it out so that I compensate for the Earth's field in the lecture theatre here. Has that gone to 0 plus or minus the last significant digit? I hope so. Now, watch what happens as I turn the current up in this solenoid. Okay, I hope you can see the field going up. You can? Yeah, good. Okay, so this is giving you a readout in Gauss, which is a nice turn-of-the-century unit for magnetic field. It's 10 to the minus 4 of a Tesla. And as I wind up the current, you can see the magnetic field in the middle. That's the Hall probe sticking there in the middle of the solenoid, and I can generate quite a respectable magnetic field. until my power supply says enough is enough. Oh, and wow, oh, there we go, and it cuts out. Okay, and we can also see this with some iron filings as well. Let me just wind that back up to its maximum, which is somewhere around 30 Gauss, I guess. Okay, so I can now put a few iron filings on here and we can see the magnetic field lines. Okay, that better do it. And you can see the nice homogeneous magnetic field inside, which is what, of course, my Hall probe is measuring. And this is the magnetic field generated by the wire alone, just the current flowing through the wire. And of course, with an electromagnet, you take advantage of the natural magnetic field in iron, and you don't have just air inside there like I have now. You put a piece of iron in, okay, so there's a piece of iron in there, and let's see what sort of field we can get now. So I'm only a tiny fraction of the current I was before. We're going to push this into overload in just a minute. But you can see it's enormously stronger now. It's gone up, it's gone up a lot. And this is because, of course, most of the work is being done by the orbiting electrons inside the lump of iron, and the original field that I showed you before, it's still there, but it's just acting like a catalyst to get all those iron atoms all lined up and pointing and working in the same direction. So most of this field is coming out of the iron in response to the field generated by the wire. And in fact, you can continue to raise the current in the coil to bring more and more of the iron atoms into alignment until, of course, eventually every iron atom in the lump of iron is aligned with the field lines that were generated by the coil itself, and the rate of increase of the field essentially stops because you've saturated the iron. The iron can't give you any more field, and any more magnetic field that you want, or that you may need, can only come by increasing the current in the wire, just the field from the wire alone. And this is a very hard way of getting a magnetic field, a strong magnetic field, because you need a huge amount of current, a brute force method. You need a huge amount of current in order to generate high fields. And in fact, most of the strong magnetic fields generated in the world today use great fat slabs of iron, great fat slabs of copper in liquid nitrogen to keep them cool, into which huge amounts of current are dumped for a short time in order to generate these strong fields. They don't use iron, they just use the brute force wire itself with a high current. And obviously, if you could replace this copper coil with a superconductor in which the current would circulate without resistance and therefore without heating, you could raise the current and get enormous magnetic fields without having to have your lump of iron in there. And without having to worry about cooling the coil, because with no resistance there is no heat. And oh yes, that's with 15 amps in there, that's lovely and warm. And that was only for 30 Gauss. Imagine if you wanted 30,000 Gauss or more. Okay, so the trick then would be to replace this coil with a superconducting coil. And of course this, because using strong magnetic fields have so many wonderful applications. And it wasn't long before people decided to try and generate these strong magnetic fields using the recently discovered superconductors shortly after the turn of the century. And they quickly ran into problems because the superconductors, the ones that were discovered 30, 40, 50 years ago, even 70 years ago, all suffered from a limitation in that as you raise the magnetic field by increasing the current around the superconductor, either by passing a current through the superconductor itself or by some other method, you quickly found that you destroyed the superconductivity. It went away. And in fact, for mercury, as little as 400 Gauss was sufficient to destroy the superconductivity. And again, this table is only the edited highlights. We find that the best one is niobium, into which you can put 2 kilogauss, which is 0.2 of a Tesla, before you destroy the superconductivity. And that's, I wouldn't really get excited about a magnetic field of 2 kilogauss. I can do that with an iron electromagnet dead easy without having to cool it down to 9.5 kilogauss, 9.5 Kelvin. So this was a tremendous disappointment. So just to summarise those measurements, I can show you what I call the superconductivity phase diagram. Right, I've got a little job for the cleaners there tomorrow. Okay, so what we've got here is a magnetic field applied to the superconductor on the vertical axis and the temperature at which you cool the superconductor down along the horizontal axis. And you find that, for example, mercury, which I've highlighted here, which goes superconducting in the absence of a magnetic field at about 4 degrees above absolute zero, can be destroyed by a relatively weak field, but you can repair the damage by simply lowering the temperature and it returns to the superconducting state. And so on. You can keep raising the field. You keep moving up this way and then having to lower the temperature. Raise the field, lower the temperature, raise the field, lower the temperature until you reach a point even at absolute zero, extrapolated to absolute zero, above which the mercury will no longer act as a superconductor. So that region there is the good bit, and that region out there is the bad bit. Anywhere out there, up there, down there, over here, anywhere for mercury, that's bad. It's only good under there as a superconductor. Out here it's perfectly normal. And again, niobium is in a class by itself. It's on a separate diagram here because it goes up to these rather stronger fields. Yeah, just fits. But again, they are not technologically very useful. You might as well just use an iron electromagnet. Okay, so there's the first problem. With even the old superconductors, they don't work at high magnetic fields where you'd like to use them. So things sort of stalled a bit there, and people looked around for ways of optimizing the material to try and raise the magnetic field, or hopefully even raise the critical temperature at which it turned into a superconductor in the first place. And simultaneously, of course, the theorists were put to work. I assume they were locked in a room and fed through a slot in the door until they came up with a theory for this bizarre phenomenon, because this was completely unexpected, and you really wouldn't expect this from the classical theories of electromagnetism that were around at the time. And just as the theorists thought they were maybe zeroing in on what was going on, a new result became available. A new experimental result became available which showed the problem was a whole lot more difficult than everyone had first thought. Because let's first of all imagine that a superconductor is nothing more than an ordinary piece of material which just happens to have zero resistance. Okay, so we can imagine a little experiment here where we start with a lump of this stuff at room temperature, you cool it down so it turns into a superconductor, and then you raise some kind of external magnetic field, and because the external magnetic field generates eddy currents, the changing magnetic flux generates eddy currents, the external field is kept out of the body of the superconductor. And then if you kept the external field on and you warmed up the superconductor, you would then find, of course, it returned to its normal state and the field was able to permeate it once more because the eddy currents died away. And in case you don't know what an eddy current is, here's a nice demonstration of eddy currents. Here I've got a piece of aluminium, which of course at room temperature is ordinary, normal, and I've got a large magnet here. And as I let the aluminium swing down between the poles of the magnet, look what happens. Whoops. What's happening, of course, is that the changing magnetic flux as the aluminium tries to swing through the magnetic field generates eddy currents, which in turn generate a magnetic field which opposes the original field from my big magnet down here, and so the motion is completely damped as a result of the eddy currents. And just to show you there's no tricks, I'll take the magnet away and it swings freely. So that's an example of the eddy current effect when you change a magnetic flux, when you turn on a magnetic field. And of course in a superconductor the eddy currents will circulate forever because there's no resistance to dissipate them. In my piece of aluminium the eddy currents dissipate very quickly because of the resistance of the aluminium. The eddy currents turn into heat. Okay, let's do another experiment where this time you start your superconductor with in its normal state at room temperature, and you put on an external magnetic field while it's in its normal state. Any eddy currents that you generate when you turn on the magnetic field will quickly dissipate because it's normal, and then you cool the superconductor down. Now when you cool it down it enters its superconducting state, but there's been no change in magnetic flux here. The magnetic field, I'm assuming, has just remained constant while you cooled the thing down. And then so you don't expect anything to take any notice, because things only take notice of changing magnetic fields, not static ones. So then you'd expect that when you lowered the magnetic field, now you're talking about a change in magnetic flux, and so you would induce eddy currents again, which would try and hold up, and would in fact hold up the field that you're trying to take away to preserve it inside the superconductor, and the eddy currents would persist forever. I guess you shouldn't call them eddy currents anymore because they're not eddying, they're staying there. And there you've magnetized it effectively. So people tried to do these, people did these experiments then with the superconductors, these ones, niobium and lead and mercury and so forth. And this is what they got. A sensational result. When they took the superconductor at room temperature, put it in a magnetic field, and then cooled the superconductor down, even though there was no change in magnetic flux, the field was expelled spontaneously from the center of the superconductor. Completely unexpected from the behavior you'd have expected with a classical zero resistance conductor. And consequently, because the field is not penetrating into the center of the superconductor, when you lowered the field, it just returned to the unmagnetized state. There's no field left anymore. And I can demonstrate this to you right now, thanks to a sample of one of the new high temperature superconductors that I have here. Not a lot left in there. It's sitting here on the bench, and it's this black disc here. It's yttrium barium copper oxide, which we'll have a lot to say about shortly, and it's got a little magnet sitting on it. So here we have a superconductor in its normal state at room temperature with a magnetic field applied to it. Let me just top up my thermos here. Whoops. Right. Okay, luckily liquid nitrogen's a hell of a lot cheaper than liquid helium. Okay, so now I will cause the superconductor to enter its superconducting state. This one has a transition temperature above the boiling point of liquid nitrogen. So remember, the magnetic field is not changing, it's a static field here. All I'm doing is cooling the thing down. Okay, it's always reluctant to cool down. It's a long way down to 77 above absolute. Okay, so we'll just let that cool off a bit. And I've got while you're watching that, I can show you another example of what goes on here, because what we've got here is something that's essentially a perfect diamagnet. That is to say, a material that when you put it in a magnetic field has induced in it a magnetic field equal and opposite to the external field. And a number of materials, ordinary materials, are diamagnets. For example, the material bismuth will be repelled from a strong magnetic field for the same reason. It has the strong magnetic field induces a magnetic field in the bismuth, which is in the opposite direction of the applied field, causing the bismuth to be repelled. And here's a macroscopic diamagnet. It's just an aluminium ring. Maybe I'll take this away now. Which I can induce a magnetic field in, which is in the opposite direction to the applied field. Okay. So you see very graphically that a perfect diamagnet is beautifully repelled from any attempt to induce a field in it. Okay, this is working beautifully now. We've just started to see the little magnet, the little disc magnet that's sitting on the black superconductor spontaneously levitate as a result of the expulsion of the magnetic field from the superconductor repelling the magnet itself. If I've got a toothpick or something, I can poke it around and show that it's actually levitating there. Okay, I've got a special low temperature comb here, which I should just be able to give that a little nudge. Okay, you can see it when the smoke clears, spinning in space above the superconductor. It's not touching the surface anymore because the superconductor is expelling its field and therefore repelling it and lifting it above the surface. There it goes. You can see it hovering there in space. Above, you can see the shadow well below it. There's the shadow. Here's the little magnet. Maybe we can make that a bit brighter. There we go. There it is, hovering above the superconductor. Okay, so this was a pretty bizarre effect. This is not something you expect to see with a classical zero resistance conductor. So the search was really on to find a theory for what was going on here. And it took a long time. It took nearly 50 years after the original discovery of superconductivity before a satisfactory theory was arrived at to explain the phenomenon. And the theory is a little bit complicated to really understand, but I can just give you a basic idea of it. It's called the BCS theory after the three guys who invented it, Bardeen, Cooper and Schrieffer, and here's the basic mechanism. They propose that when you cool a material down so that it enters a superconducting state, the electrons passing through the material change from being an object which obeys the exclusion principle to something which no longer has to obey the exclusion principle via the following mechanism. Imagine you've got an electron here, electron A, passing through a crystal. The electron has a charge of 1 unit minus, and it attracts towards it all the host atoms of the lattice. So as the electron passes by, it leaves behind it momentarily a little cluster of positive charge, just a tiny little cluster of positive charge, as all the atoms, a lot of the neighbourhood atoms, the ions of the lattice, try and go towards it by the electrostatic force. And then sometime later, imagine a second electron passes by before this little bit of charge dissipates. Then when the second electron passes by, it will be sensitive to the slightly increased region of positive charge, and it'll be deflected a little bit. And so you can say that electron A and electron B are kind of coupled together. They're coupled together via a disturbance in the lattice. And only certain lattices allow this to happen. The lattice has to be very responsive to the perturbation of just a single electron passing by, and it has to hang there long enough for a second electron to come past in order to feel the effect of that perturbation. And we talk about anything that disturbs the lattice as a phonon. We call that a phonon. That's just a technical name for a disturbance in the lattice. And so we talk about these two electrons are now bound together by the exchange of a phonon through the lattice. So what we've got here is, instead of having two individual electrons which are free to propagate through this lattice independently, we now really only have one new particle, which is two electrons plus a phonon, which is called a Cooper pair. A Cooper pair is what carries the supercurrent through the lattice of the metal or the material that's superconducting. And the reason why this object goes through without resistance is kind of easy to understand on one level and a bit more sophisticated on another, in that you can imagine that if this electron A here, scatters from somewhere in the lattice, and in other words experiences some resistance, it triggers this disturbance which we've called a phonon, and then when this one comes past, it picks up the phonon. It picks up the phonon that the first one generated and recovers the momentum or the energy or whatever was lost in the first scattering event. So the net change in momentum or energy of the pair A plus B is equal to 0, because what A lost, B recovered. So we don't have any resistance anymore, because we don't have any change of energy of the electrons. We don't have any Joule heating of the material. It's all recovered by the fact that these two electrons are paired together. That's a slightly more sophisticated way of thinking about it, is that these two electrons together no longer have to obey the exclusion principle, which keeps all the electrons up in a high energy state, because you've got a composite particle which doesn't have a spin anymore. The spins cancel out via the mechanism of the exchange of the phonon, and such a spin zero object can condense down into a lower energy state, which any other spin zero object is also free to occupy at the same time, unlike two free electrons piling into the region around a nucleus, for example. They all have to occupy different states, and so they'd all like to go into the lowest energy state, but they can't, because electrons don't work that way, and so the electrons stack up, and before you know, you've got the whole periodic table and the whole field of chemistry. But down here, a Cooper pair experiences no such inhibitions. All the Cooper pairs pile down into the lowest energy state available, and in doing so, all the electrons, all the Cooper pairs become correlated, and you sort of have something like a giant electron molecule in the lattice, which just propagates through as if the lattice wasn't there, because it's not energetically favourable for any scattering events to occur. However, this pairing mechanism is obviously very delicate, and it doesn't take very much thermal agitation of the lattice to to break the bond between the two electrons. And so it's not surprising, therefore, that the superconductors only work at very low temperatures. Now, let me return to the story about the quest for superconductors that had better properties than the ones that were first discovered, the pure metal superconductors. Here's a picture of the magnetic field induced in a superconductor by an external magnetic field. That's what I've got along the vertical axis, the induced field. And along the horizontal axis is the field that was responsible for inducing that in the first place. So you can see that as you increase the external field, the superconductor responds by cancelling it out, and it continues to do so until it can't do it anymore, until it's no longer got any capacity for cancelling out the external field, and bang, it drops down and becomes normal again. So once again, down here in the low energy, in the low field situation, we've got the superconducting state again, and then once you've raised the field above the critical field, the superconductor can't keep the field out anymore, and it goes normal. The resistance returns. Cooper pairs break up. And that's the situation for just about all of the pure metal superconductors. However, the intensive research that went on at the time soon found a class of superconductor that was not, did not suffer from such effects. And these superconductors kind of had a little bit of self-sacrifice, and here's the magnetisation curve typical of one of these new old superconductors, or old new superconductors anyway, the one before 1986. What happens here is that as the applied field increases, the superconductor hangs in there and is able to cancel it out until it begins to get overwhelmed. It begins to get overwhelmed, but instead of collapsing in a heap all at once like the old type 1 did, it actually lets some of the field in. It lets some of the field in, but still, and sacrifices some of the superconducting state into the normal state, but there's still sufficient superconducting state left that it still has zero resistance. And so we have what's called this vortex state, which is what happens after you lose the pure superconducting state, until finally you keep raising the external field until even then the vortex state can't hold the field anymore. And I think I've got a picture of this, a picture of what happens. Okay, that's one of the new ones. It might be up here. Yeah, this is it. Okay, here's the picture of the vortex state. What we see here is the entry of the magnetic field into the superconductor along these little vortices. So you imagine you're looking down the direction of the magnetic field that's been applied to a superconductor, and here the vortices have begun to allow the magnetic field to penetrate into the superconductor, but surrounding them is still superconducting material, so the resistance is still zero, because the zero resistance material shorts out the normal material in the vortices. And here's an actual picture of the vortices in a metal superconductor. You can dust the surface with a bit of iron powder and it sticks to the place where the material has gone normal, where the magnetic field is, and you can see this nice vortex lattice of vortices where the material has begun to break down, but it still has zero resistance. And this picture up here shows a close-up of the surface of a piece of lead which has been cooled into its superconducting state, and here you can see individual magnetic flux lines emerging from the surface of the lead. So that's like a side view, that's like a top view. And the mechanism to make those lines visible is, I won't go into, that's very technical stuff, but it's an ingenious, done in an electron microscope in a very beautiful and ingenious way. Okay, so suddenly we began to have an industry of superconductivity, and here's a picture of one of the early practical superconductors which could generate quite strong fields. It was found that the pure metals, all you had to do was contaminate them with things, and they turned into this type 2 material with this vortex state. And so these curves here, A, B, C, D, is for lead with increasingly higher contamination of indium. And you can see that in the alloy D here, the vortex state exists way up to 3.5 kilogauss before the vortices coalesce and let the field in, and it turns into a normal material again, which is getting up there, getting to be quite respectable. Pardon me. And here's a picture of a vortex lattice in one of the new superconductors, which we now need to talk about. Because despite the best efforts of several decades of intensive research, still by 1970 or so, optimizing the vortex state in the superconductors has still only given us niobium-3 germanium, a compound of niobium and germanium metal, which went superconducting just above the boiling point of liquid hydrogen at around 20 Kelvin above absolute zero, which is not terribly spectacular, but nevertheless, if you cool this stuff down to liquid helium, it was capable of generating quite respectable magnetic fields. And in fact, most of the technology today of high magnetic field superconducting magnets is based, in fact, on niobium-3 tin or niobium titanium, because of their excellent, well, relatively excellent metallurgical properties. But, of course, in 1986, things changed dramatically. A whole lot of new compounds suddenly became available. And to give you an insight into what happened in 1986, I'll just tell you a little bit about these new compounds. The guys who discovered them, Bednorz and Mueller, were experts on a material called strontium titanate. And strontium titanate is used between the plates of the capacitors in your Sony Walkman, so that the capacitors are small enough that your Sony Walkman fits in your pocket and you don't have to push it around in a shopping trolley. It is a material which polarizes really easily. You just put a little bit of an electric field on it and bingo, all the molecules polarize to try and cancel out the electric field. And it has this perovskite structure named after a Russian count who was actually also a geologist in his part-time. Or maybe he was a count in his part-time, I don't know. But anyway, there's something good about this stuff in that it's fairly flexible. The electrons can move around fairly easily, perhaps. And they thought maybe they could make a superconductor out of some variants of this. And the key to it, the key to their reasoning is a little bit technical, but they figured that if they put some copper oxide in there, the copper oxide, which normally is not a very interesting material, it doesn't conduct electricity very well, and it's an anti-ferromagnet, indicating that the electrons around are sort of all anti-correlated, so there's no internal fields or anything like that. But they figured that if they could just bleed off some of the electrons from this copper oxide in the perovskite structure, they might be able to loosen it all up a bit and turn it into a superconductor. And they had good theoretical reasons based on their experience with strontium titanate why that might be possible. So they got some copper oxide and tossed in a bit of lanthanum and strontium, and bingo, they hit the jackpot. Straight away they found, quite a respectable critical temperature down here. You've got to keep it in mind that this perovskite structure is actually a ceramic, it's not a metal. And it does conduct electricity okay a bit at room temperature, but of course it went superconducting, their first sample, which was a great surprise, really, considering that it's a ceramic. And then by optimizing the stoichiometry, by optimizing the compound, they soon pushed the critical temperature up to above 50 Kelvin, which would have been miraculous for a metal. It was absolutely astounding for a ceramic. And this picture over here shows, gives you some idea of the structure. We've got a whole lot of copper atoms. These are these greenish ones down here, and they're surrounded by these pyramid-shaped structures of oxygen. These ones here are oxygens, they're the coppers in there, and there's another plane up here. And it's these copper oxide planes where part of the 2+ valence of the copper has been bled off by all this other stuff, all this decoration, barium, and in this case thallium, and a whole lot of other things, is bleeding off a little bit of the valence, so the copper valence is a little bit greater than 2, which is responsible for the mechanism of the superconductivity. This is the engine room of a superconductor, the new superconductors that were discovered in 1986. And in fact, the supercurrents, the Cooper pairs, only propagate along these planes. You do not get superconductivity at right angles to these planes. And that was new. That was new. And so there the matter rested until a guy called Paul Chu, that was at 50 Kelvin, a guy called Paul Chu in Texas, who's an expert on superconductors. He figured that, normally if you take a superconductor and you squeeze it, its critical temperature goes up a bit. So he tried squeezing this material by putting some smaller atoms in, and bingo, he put an yttrium in instead of a lanthanum, and wow, it went up to 90 Kelvin. And then other guys started playing around, and before very long, 1993, we're up to this thallium, barium, calcium, copper oxide. It's still essentially copper oxide with a few helpers, which is the record now, somewhere around 130 Kelvin above absolute. And this guy Chu is a smart guy. when he discovered the yttrium barium copper oxide, he sent a paper off immediately to establish his discovery. And this was the paper as it arrived at the journal to be refereed. And the refereeing process of a scientific paper is supposed to be confidential because you're looking at new results. And here it is, superconductivity at 93 Kelvin in a new mixed phase ytterbium barium copper oxide compound. And legend has it that a whole lot of very prominent laboratories in the United States began immediately ordering large quantities of ytterbium before the paper appeared in press. And then just before it did appear in press, Chu, spotted that typographical error, oh dear. And put it back to yttrium where it should have been, and rang up and said, please explain. So that was an interesting test of the refereeing process of these journals. Okay, so it's time now to see what these new superconductors can do and what sort of applications they can have. Well, the new superconductors turn out to behave a bit like the old superconductors. Here are the old superconductors here with the pure superconducting state. Here's the vortex state where the vortex line, the field begins to penetrate through the material, and then finally here's the normal state as you raise the temperature or raise the magnetic field. Well, the new superconductors are a little bit more complicated. They also go through this vortex state, but they have this new state here called the vortex liquid. And here the superconductor kind of sacrifices itself even more strongly than it normally does in the vortex solid as a consequence of their remarkably high critical temperatures. And the vortices, instead of being locked in place, actually wander about under the influence of currents and what have you. So it's, all the vortices are jumbling around. And even though it's still a superconductor, the jumbling around of the vortices in the vortex liquid here dissipate energy. And so you can find you've got a superconductor in this state here at a particular temperature and a particular field, which has got a resistance greater than copper at the same temperature, even though it's still superconducting and it's still Cooper pairs carrying the currents. So that is a real problem because that's the high temperature region where you might want to operate these things in liquid nitrogen. So this has so far impaired their use as in technology. However, there are some devices on the market. This is a close-up of what's called a SQUID, a superconducting quantum interference device. This makes use of one of the delicate properties of a Cooper pair that, as with any quantum mechanical object, that it can tunnel through thin layers of insulator. And tunnel through, even though classically you'd expect it to be forbidden, an insulator is an insulator, a quantum mechanical object can tunnel through providing the insulator is thin enough. And in fact there are two there are insulating regions. The supercurrents come in here, go around in this spiral and come out here, and the only way they can come out again is to go through these forbidden regions, which they do. And this tunneling process is in fact very delicate and is easily disrupted. And it can be disrupted by tiny, tiny magnetic fields because this tunneling process is so delicate. And in fact, the magnetic field from the human brain is sufficient to disrupt the tunneling process that allows the supercurrent to get around this loop. And so here we see an application of these SQUIDs, superconducting quantum interference devices, for mapping brain magnetic fields from just thought processes running around. And this person is sleeping easily, knowing that that's only liquid nitrogen in there, not liquid helium like it would have been a few years ago. But of course, the most exciting applications are in the high magnetic field areas where you'd like to make frictionless trains. And this is in fact a prototype of a frictionless train built by the Japanese using the old superconductors. And these frictionless trains are suspended by the Meissner effect, by the diamagnetism of the superconductor, which I just demonstrated, and in principle can travel at very high speeds using linear induction motors. They're suspended on the induced magnetic field of the superconductor inside the train. So you put an AC field on magnets that run down the side of the track so that you always have a north pole repelling a north pole, south repelling a south. And you can propel this thing. You don't need a motor in the train. The motor is the track. The only trouble is you need enormous magnetic fields to suspend something as heavy as a train without, without the wheels. And the new superconductors probably aren't going to be able to do the job, unfortunately. There's an interesting story associated with this train. Because it had to be very light, because the fields required otherwise would have been too strong, they made it out of a magnesium alloy. And one day after a test, the train caught fire. The magnesium began to burn. And it burned for a while, and then the fire brigade arrived to try and put it out. And it's very hard to extinguish a magnesium fire because magnesium burns with tremendous enthusiasm. And one of the firemen got his axe out to try and chop away some of the burning panels. And of course, he went to chop it, and then clang, it stuck onto the superconducting magnets. Even though the train was on fire and the current had been turned off, the current was still circulating in the magnets, and because of the super insulation surrounding the liquid helium and all that stuff, the fire had not been sufficient to extinguish the superconductivity, to boil off the helium. Further applications, possibly for the new superconductors with a bit more work, are magnetic energy storage systems where you have a gigantic loop under the ground of the new superconductors, carefully encased in aluminium, and there's no problem about the aluminium shorting out a superconductor because the aluminium is normal. The superconductor has zero resistance, and in fact in some of the early superconducting magnets, gold was judged to be an appropriate material for insulating the windings. You can store enormous amounts of electricity in these proposed magnetic energy storage systems by pumping current in so it circulates forever until you want to tap it off and use it. You have to make them tremendously strong. They have to go underground because of the magnetic forces involved. And if you ask the chairman of Professor Klein, he'll say, well, why don't you just use compressed air in the first place? Well, I tried to cook my toast this morning with compressed air and it didn't work. I prefer to use electricity. Okay, and there are lots of other applications. An interesting one is magnetohydrodynamic electricity. Oh, I should talk about the ship first because I've got another nice demonstration here on the ship. If you pass an electric current through seawater in a strong magnetic field, you can push it along. You can push the magnetic field acts on the current passing through the seawater, and the seawater is pushed back. And I've got a demonstration here of what happens if you pass an electric current through mercury, which is in a strong magnetic field. You can just see a little puddle of mercury in the top there, just in there, well, just here, right there. And I'll now pass, it's in a little U-tube which passes through a strong magnet. And if I just run a little bit of current through the mercury, well, when I say a little bit of current, I actually mean a humongous amount of current. Okay, we're starting now. 20 amps. 25 amps. Okay, we're away. We've got a current of mercury flowing around in a loop, powered by the magnetic force on the electric current that runs through the mercury. So if you do the same job on seawater, although seawater doesn't conduct electricity quite as enthusiastically as mercury does, so you have to use higher currents or higher fields, you can use this to push jets of water back and make a ship that doesn't need a propeller. And the Japanese made one of these things using the old superconductors as a prototype. And of course, if you saw the film Hunt for Red October, the submarine in that film also used the same technique. Magnetohydrodynamics is a possible way of generating power. I might skip the SSC, it's dead. Where you, let's see, I'll just, oh, here we go, there it is. Where you can pass hot gas through a strong magnetic field, which will then separate out the positive and negative ions in the gas stream. And this shows the process. You've got burning gas here, positive and negative ions flying down the tube as a result of the heat, and the strong magnetic field separates the positive ions and the negative ions, allowing you to generate electricity. And this was a prototype plant the Americans built and then gave to the Russians. Probably a story there somewhere, where they made this big grey thing on the left there is a superconductor for separating out the ions for making electricity, and it burned up about 10 times as much energy as it produced. Okay, so back to the new superconductors. I just want to finish off by saying a few words about what's going on in Australia with the new superconductors. There's a big laboratory based at the University of Wollongong, but involving a collaboration of many tertiary institutions around Australia, and also several far-sighted industrial concerns, and a couple of government organisations dedicated towards trying to push the new superconductors into a useful commercial form. And this shows one way of doing it. You can take the superconductor material, which initially looks like this, and this is bad because you've got a lot of grains where you've got to do a lot of tunnelling to get from one to another. It's much better to look like this, and put it inside a tube of silver, which you can then draw down into a tape, such as being shown here, rolled onto a spool, because you've got to remember this stuff is a ceramic. And this shows a cross-section of one of the tapes fabricated at the University of Wollongong. Here we see the black superconducting material, a ceramic, surrounded by the silver jacket after the drawing and rolling process, and then you can make magnets and other applications. Unfortunately, all the problems I've spoken about with superconductors, the vortex state and so forth, means that for most practical applications, for the trains, for making electric motors, for magnetic energy storage, the new superconductors, here are the best ones from the University of Wollongong, are still not high enough magnetic fields, not high enough currents to get you into these useful regions. So unfortunately, the only thing they've been used for commercially so far are the squids that I've mentioned already. So a considerable amount of work has to go on before we can try and raise these things up into the useful region. But I have to keep it in mind, these things down here are all working at liquid nitrogen, whereas the old superconductors all have to work at liquid helium. So it is progress. What of the future? Well, if you look in the scientific literature, hardly a month goes by without a diagram something like this. Professor XYZ from University ABC has a bismuth strontium calcium oxide film, and when he cooled it down, it went superconducting at 250 Kelvin. Astounding. He then warmed it up and cooled it down again and didn't do it anymore. Another situation for the Journal of Irreproducible Results. And again here, another sample, this time mercury, barium, calcium, copper oxide. Transition temperature somewhere above 220 Kelvin, but unfortunately you warm it up and cool it down, it didn't do it anymore. But this is very tantalising, that maybe there are higher temperature superconductors out there, and maybe one day we will see a superconductor that will work at a useful field at even room temperature. But it's hard to imagine how the pairing mechanism, the Cooper pairing mechanism, could work at a material at room temperature, because any material that was flexible enough to allow the electrons to bond together would surely fall apart when you heated it up as high as room temperature. But I'm not prepared to rule out the possibility altogether. So in answer to my original question, the new superconductors, are they a new industrial revolution? I reluctantly have to conclude that the answer is no. But I'm prepared to be optimistic and modify my answer a little bit and say not yet. Thank you very much.
Well, thank you, David, for a brilliant exposition of this interesting field. Are there any questions? So, you just showed a graph a moment ago which shows using superconductivity about 4% of all these fields.
Yes, indeed. No, 1 Tesla. 1 Tesla. Oh yes, under some conditions, thin films and so forth, you can get rid of the, freeze the vortices and what have you, and you can get it up higher. But the problem is a thin film is not useful. You've really got to have a wire which you can then start doing things with. Yeah. Pardon? Yes. Well, yes. It's the problem is getting it into a useful form. This is not in a useful form. Usually is a thin film. And I think this curve might be a bit optimistic too. I'm not very well up on the technology of low temperature measurement, but I know that Onus was able to calibrate his platinum thermometers against, I think it was a gas thermometer. I'm not exactly sure how it worked, but this gas thermometer could be absolutely calibrated, I guess, on the volume of the gas at a particular pressure, for example, would return a temperature against some extrapolating downwards on the basis of ideal gas law appropriately modified and so forth. And then he could calibrate a platinum resistance thermometer which he could then use for other experiments.
I think, for example, the materials which are not superconducting, there's a lot of these, they do carbon, start from really useful, converting all the way down to carbon thermometer, which is the early days. Ordinary aliphatic resistance which comes out of carbon resistance
Actually, carbon is a superconductor. Buckyballs. Buckyballs go superconducting. Well, you have to keep producing results, of course, and that's why we always see this stuff going on all the time, because that's obviously worth another 100,000 to find out, purify the material or whatever. At the moment, I don't think the funding has peaked. I think people are still optimistic about that better and better processing steps will be found to solve this problem of the vortex melting and wandering about all over the place, different grain sizes, stabilizing the material with extra elements. For example, you put lead into this material, it stabilizes a high temperature phase and so on and so forth. I don't think it's even plateaued yet. It's still very exciting, a lot of activity in this field. If you pick up any journal on material science, you still find a huge number of papers on superconductors, almost as many as on, say, silicon, which is obviously a popular material as well.
If I may answer that after these departments. First of all, let me say that after 1986, about 1/3 of the world's solid state physicists were all suddenly switched to high-QC superconductivity. We have a few very good solid state physicists. Said, all right, what are we good at? Said, well, we're good at analysing structures of superconducting material, and we, along with everybody else, went around looking for money to undertake this kind of work. Well, to cut a long story short, we were on to that and did get it sacked. certain other people talking with Wollongong was prepared to undertake all sorts of promises to deliver the state high current capability and so on. They haven't got there yet, but they've collected an awful lot of money. In terms of scientific knowledge generated, the largest number of papers in this field in Australia come out of this school, Dr. Peter Goodman in Australia. But there's no money in that, they're just finding the structure of barium, copper, distillate, all this sort of stuff. It's a very significant contribution to do the structure of materials that do and don't do the conduct, how to do the temperature and so on. And one day we may just understand how it works. But the money is elsewhere. And there's sort of a curious relationship that these things happen 20 years later. 20 years after the discovery of solar sensitivity, people started taking photographs of it. 20 years after the discovery of laser, you got one in your house and so on. So yes, 20 years time, 1986, I guess, the year 2006, I think some tremendous industrial breakthrough. And suddenly, what do you mean by breakthrough? It will break through into people's consciousness. But we know all about it 20 years later. Yes, Richard.
Yeah. Well, it's still BCS, Bardeen, Cooper, Schreifer, still. Originally, when these materials were first discovered, people said, oh, no way can that delicate Cooper pairing mechanism possibly work at such high temperatures, because the thermal agitation of the lattice would be guaranteed to disrupt it. But no, it's not true. It still works, only along the copper oxide planes, though. So there has been, as far as I know, from the literature I'm familiar with, there is no serious competitor to the BCS theory. The same theory that applied to the old materials, still valid for the new materials. Sure, there are a lot of tweaks along the way. I mean, the phase diagram is obviously pretty radical compared to the old stuff with this vortex liquid. And in the details of this, other people other than BCS developed theories about the formation of the vortex lattice, even for the old stuff, the Russian guy in particular. And that theory maybe doesn't work so well over here for the liquid. So in that sort of sub-area of the field, there's a lot of activity. But in terms of the overall, the big picture is still the BCS theory, still going strong. I don't think so, no. I think the reason why Bednorz and Mueller got their Nobel Prize was because of this reasoning, associated with why the copper oxide was going to go superconducting in the first place. This idea of the fractional valence and pulling a few of the electrons away in the perovskite structure. That was the clever bit. And they were lucky enough that, of course, it worked. It wasn't luck. They'd been studying these materials for 20 years. For dielectrics in capacitors and all sorts of other things, piezoelectric materials, all the same class of stuff. And in fact, the Nobel Prize Committee did a very interesting bit of politics there, because you could argue that maybe Paul Chu should have been involved, because his key reasoning led to the idea of raising the pressure by shrinking one of the constituents of the lattice. I mean, if you look on this diagram, this was Bednorz and Mueller down here, hey, but this was Chu up here, right? So that's bigger than that, so that should be worth a Nobel Prize. But, and it was very interesting, the Nobel Committee moved very fast, and it was in 1987 that Bednorz and Mueller got their Nobel Prize, whereas Chu's paper was published in March 1987, and you can't get a Nobel Prize in the same year where you did your breakthrough, because there's not enough time to go to the referees, etc., get the King of Sweden into it and all this sort of stuff. And so Chu could not have won the Nobel Prize in 1987. So there was no argument that Bednorz and Mueller in 1987 were the only ones for this little step here to get the Nobel Prize. And of course in 1988, when Chu would have been eligible for the Nobel Prize, hey, that was superconductivity, that was last year's Nobel Prize, this year there's some other breakthrough. So it was a very political, very savvy. I admire that, the skullduggery that presumably went on.
I just noticed something. Received 6th of February 87, revised manuscript received the 18th
Yeah,
of February and
yes.
published on the 2nd of March.
Yeah, it's that typo.
Even the journals
Yeah.
know how to move fast when,
Yeah.
when there's something really
Oh well, I mean, this was hot stuff. I mean, I went to a conference shortly after this was publicised, and in fact ended up having dinner in a Chinese restaurant out the back of Disneyland with Paul Chu, which was quite interesting. And it's a complete digression of the story. But I've never seen anything like it. I mean, there were people running around this conference carrying thermos flasks and brandishing these little black discs everywhere and saying, "Hey, look at this, because being able to just demonstrate the Meissner effect, almost in your bare hands, that was completely unprecedented. I mean, this is really an esoteric kind of thing here we're seeing here. This is not some trivial demonstration, even though it looks like it. This is really fancy stuff." And it was just people were piling in to look, and one guy even had a little row of magnets with little cardboard trains glued to the back of them, and he was zooming them around. Oh, just absolutely amazing. Never seen anything like it. Yeah, dead easy. This stuff's dead easy to make it. People make it in high schools and what have you. Just buy the chemicals, you grind them up, you heat it up in the school's pottery kiln for overnight just in air, because you need a lot of oxygen in there in order to make the fractional valence for the copper, and away it goes. Get some nitrogen from the hospital or wherever you buy it, you just order it. It's not very expensive, and you can demonstrate it. Yeah, you don't need any sophisticated stuff. I would do it, Graham, but unfortunately I don't have any way of retrieving the aluminium ring from the nitrogen after I've dropped it in. Unless you'd like to come in and... No, I'm afraid not. No.
For the benefit of the audience, we have done it. It's not easy to see.
Not really essential. Not really essential.
In the railguns, I think eventually those things vaporize and plasma.
Similar principle. Yeah.
Well, if there's no more questions, not only have we some very nice physics, we also had a lot of fun. Thank you very much indeed, David. Please don't forget next week the extra July lecture that should have happened a fortnight ago. I hope to see you again here